Stay in the cut on the north side. Hella points, trigger fingers on my fucking foe. 5 demons rising out the crypt. I smoke me a fat line, never gave a fuck. Grew up by the mud, pull up then I pop the trunk. Grew up with the fucking robbers, always kept a mask on. Motherfuckers gon' die if we keep the mask off. Suicide when I ride, bitch, scarecrow to walk the shadow. Mozart with no piano, kill when I'm sleepy hollow. That mystic motherfucker that's addicted to prescriptions. Xanax for the panic, mental problems, you can add that. Multi-million own business, you just signed a deal, bruh. 3 years past, still broken, you ain't paid up. Dollars I ain't touched yet, burning for the fuck of it. Infamous lunatic, you just sucked it. Cut up with the death wish, raised with the savage live. Straight out the death pit to keep alive the 666.
Ruby such a misfit. Hollywood, Babylon, can't resist it. Fuck a cop, bitch, I'm ducking all these piglets. 7 war, be my motherfucking district. Yeah, I still got my motherfucking wrist split. Bleeding like a piss, bitch. Screaming I'ma hit licks. After licking hits of acid, then the fucking split lips. Wig split, just a fucking tidbit. Dig it from ingested pill, bitch. Blue bill, sick of snorting powder. I'ma ditch this. 104, 520s, T. Say keep testing my monies. Now I'ma dip quick. Find me a thick bitch. Tick grip, tip grip, dick spit in the thick kips. Fuck with me, bitch, I'm a fucking addicted. And I don't really give a fuck what it is. Told you already that Ruby can't resist it. Big clip to my head, watch that shit drip.
They know the bait was suicide. Too deep when I ride. Ruby getting out for the pills that I supply. The screws are bound, flat tires in a 06 Chevy. Looking like I'm Bloody Mary, sipping codeine and berry. I'm down to doggo when I smoke up and I'm creeping like Frank. Raising that chopper right at your face and after that I go blank. Cause looking at off the hinges with syringes shooting on my veins. Rather be left alone, I don't care to know your name.
Здорово, пацаны.
Ну тебе не хворать.
Watch me flex like I'm in the next. Like the job was next in line for heaven, but then I ingested the devil. Come full of that fucking insecticide. The shakes inside my dead body. Ironically, after I do was identified, possibly got a piece specified. Cause the work that was intensified. Tracking the lick, they made a mistake because young big was recognized. The sun turned black, the sky replaced by the face with giant red eyes. Christ, you not compare again. I say we breaking bread and wine. Suicide boys can relate to the revelation because we did it out.
Wanna go.
New Orleans is ruled by thugs even more ruthless than LA's most violent gangs.
You know, the Crips and Bloods try to establish themselves here.
All I see is scrubs. Face me, mud. On a couple drugs. Smoke amigo plug. FDP my blood. Greater fucking guy. Or stay in your lane.
Never hide, just make it. Hate this pain, hate this guy. Take these shoes as a day. Or you're flowing through my veins. Love remains that make that stain. Y'all look good as cellophane, man. Insane. Real place like it's on your fucking brain. I said, fuck, we got a problem. Fuck you gon' do with.
I think that just a persona. And I'm the final. All it says to make you mad. I know you want some. Rollin'. Got a ounce of that cold white snow flowing. River road, shot it, y'all crack, swan chosen. Slit told the AK-47, stolen, more than Joseph.
All of y'all are oversaturating, premium bet. Bitches FDP all fucking day. All y'all look the fucking same. Fuck the fame, fuck the lane. Bitch, I'm about to swerve into the toll booth and scrape the chains. Bring out your dad and blame it on yo. Bitch, I pull up. Okay, now I'm by my right leg till I say okay. K9 on his hind legs, ripping off your face. All I gotta say is G590 to the grave. One color, two numbers, three fingers in the sky amongst the thunder. I'm like, fuck the youngest, I'm bring the ruckus, somebody. Fuck your bitch, you swear she's something, some of the covers on me. I'm a hellbound, shorty wanna die. I'm a hellbound, shorty said she might let them bells bound. Shorty wanna cry, I'm like, fuck it every night. Keep turning black, I close my eyes.
Maybe next time somebody watch me, just maybe.
Hey, couple chickens with the Glock on my side. Riding, hanging out the window, screaming who wanna die. Savage left, Alec with 100 bad habits. Say I need prayer, all I need is my ratchet. I swing with the blade, then I pray over dead prey. Banging great, on my grave, Millie right. Stop, I say, what that mean? I don't know. Till about 4 seconds, so they sipping lean. Dying slow, drugs make me feel okay. I got cash, and cars and bras. Hit that 7-figure mark without an A and all. Scarecrow walking in the fog. Life got worse than it was before.
I'm trying to see the road, but all I can see are 4 horsemen coming closer to me. I think I'm about to die with it. Swerving on the motherfucking bitches, they my time. Let the road blow up first, then I might just close my eyes. It's all I really want. I don't like the universe, won't know this bitch. You just another line. The sun will rise, the stars have already died.
Come on, kick that. kick you, piece of shit.
See the reaper creeping as my blood is seeping. Sleeping deeper through the night so I can face my demons. Weakness seems to be that I cannot stop breathing. Death keeps cheating on my life, but now my soul is feeding.
Laying into the fleeting, nothing in the street. Screaming and needing, yelling and pleading. The things ain't as they seem. And because sneaking and tweaking because I can't stop seeking. This pain is torture, a horror that I'm always conceding.
You must learn to obey. You must learn to obey. You must learn. You must learn to obey.
Time out, guys.
Eternal rest, the bloody mess. Keeping a motherfucking devil hot. Satanic mentality happily making the bodies drop. I'm on the block, circling cops, ready for dead demise. Screams resonate through the night so I can't close my eyes.
Hard to swallow when the hollows enter through your throat. Lately I wallow in my sorrow cause I cannot cope. The dope that coke
Why don't you time out?
that feels that extra smoke. The rope that choke the pain away. I'm broken till I croak.
Baby, let me get the keys to the Rover truck. Baby, let me get the weed to smoke for us. When these suckers leave, yeah, we can smoke it. Blind the fuck, I'm busting nothing now. It's time to get the fuck about my grip. Yeah, it's a couple bucks. Bitch, I'm hiding up, creeping out the cup. Dust seeping out my cup. With the shot because you might escape the time begun because I'm busy puffing blunts. But soon enough, you'll come back round. You screaming, like me up, please box me up. I got you sucker, start the flame and turn your body up. Smoke your body in the blunt, got me yours, I light it up.
Release
3 hours to the flame.
Reprograms your brain. Product.
This is fun.
Walk in with a dead bitch
Blunt between my lips and riding with the bitch the size me. She ducking out, she trying to sleep. I'm ducking out, I'm trying to see the road, but all I can see are 4 horsemen coming closer to me. I think I'm about to die, we'll see. Swerving on the motherfuckers, bitch, it ain't my time. Let the road blow up first, then I might just close my eyes. It's all I really wanted my whole life. The universe won't know this bitch, you just another line. The sun will rise, the stars have already died. Creeping as my blood is seeping, sleeping deeper through the night so I can face my demons. Weakness seems to be that I cannot stop breathing. Death keeps cheating on my life, but now my soul is feeding.
Leaning to the fleeting of and in the street, screaming and needing, yelling and pleading. The things ain't as they seem. And Nika sneaking and tweaking because I can't stop seeking. This pain is torture of horror that I'm always conceding.
You must learn to obey. You must learn to obey. You must learn. You must learn to obey. Throwing smoke. Deploying flashbang. Laying down smoke. Grenade out.
Making the bodies drop. I'm on the block, circling cops, ready for dead demise. Screams resonate through the night, so I can't close my eyes. Hard to swallow when the hollows enter through your throat. Lately I wallow in my sorrow, cause I cannot cope. The dope, the coke, the drink, the lean, the pills, the extra smoke. The broke, the choke, the pain away. I'm broken till I croak.
Let me get the keys to the Rover truck. Baby, let me get the weed to smoke for us. When these suckers leave, yeah, we can smoke a blunt and fuck. I'm busting nothing asses. I'll be get the fuck about my grip. Yeah, it's a couple bucks. It's a mighty nut, creeping out the cup. Blood seeping out my cup. With the shot because you might escape the time begun because I'm busy pumping blunts. But soon enough, you'll come back round. You screaming, like me up, please back me up. I got you something, start the flame and turn your body in the dust. Smoke your body in the blunt. Got me yours, I light it up.
Free me. Release me. Burst into flame. Reprogram your brain. Product. Come on, chop. Smoke. Incendiary. Throwing flashbang.
So dramatic in a manic, feeling panic. I need a Xanax, pass it as I hold it, real slowly, lonely, looking ghostly, surrounded by smoky mirror images of a fictionist over me. Don't give a fuck me, I'm drug and dealer, R.I.P.
Слева. Сзади.
Блядь, 96.
Обидно.
Take a hit, the ass have been a while since the trip. Now I see you know the shit, brain glowing, everything was bending in the same motion. Roll the blunt, I take a hit, start staring at the smoke. Gas and twist and disappears. Peer pressure don't affect me, bitch. I take drugs on my own. Pop up Perkins, throw some coke. It feel like my heart is broke because I get fucked up when I feel alone. I'm choking on this podium, I'm hoping that I don't breathe, bitch. I'm dope back like you know me. Shoot me up so I can know deep.
Яма, яма.
Тетрис.
Must one person's triumph be another's humiliation?
Of course.
Another day, my demon does every day that I'm wasting mountains of regret. So I tell myself it's okay day after day to make all these reckless days. You can better yourself. I know I'm wasting my breath.
Идите, я охраняю шоу.
Step into the mind of a cutthroat. If the streets cold weather all alone, blackness, gray hair, just know. Feelings OD and followed by crows. Call list overflow with highlights. Drug help, mental suicide. Feel tight, feel dry, then you know it die. Pride, close eyes and you start to cry. Swear I spent a lifetime trying to get it right. Still isolated, still out of sight. Keep my dress swinging like they in a fight. I just wanna kill everyone in sight.
Take the money, take the bitch, take the drugs, take the gold. Baby, let me decompose. Lemonade sip, shade spit. I'ma see you one day, that's a promise.
Green, go well. Nice. Went green.
Sipping lean, caffeine with codeine. I'm smoking nicotine. PCP, pills in my cuisine. I'm fucking Drake this way. Risk dismay, suicide, renegade. Pop a couple waves up in my grave. Carving my skin with a blade. I don't fuck with skrillers. No drug dealer, stealer with the sealer. Sick of that always wreck. Bitch get checked. Grapevine 9 to 6. Chopper make them wet. Watch me flex. Y'all just second best, never second guess. Manifest, triple six till death.
We ain't my motherfucking true name. If I roll it down and we can bust into a blue flame. Blue gang banging out cruise lane. Body in the suitcase, polo body bag full of bootlegs. Two-face bitch, sick of duck. Got your bitch lay your goose eggs. Two fangs, going got a toothache. Tie me up like a shoestring. Let the new sang. Got in my box, I need a new frame. Ruby the cherry, ain't got a pocket full of fruitcake. Bruce Wayne, wanna be. Fuck with me, I'll probably give you something free. Honey surrounding around me, cause I'm buzzing like a fucking bumblebee. Most of my raps are fucking tongue-in-cheek. Fungus in my lungs, got the rings of crumbling weed. Another day, another feat. All the fucking dirt, you will find me underneath. With the active phase, pop 2 pills with Gatorade. Round my decade, Gator phase. Might pop your more on a later date, but I don't know. Young stroke, how they go with the flow. Bring her home backstage, she'll tell me everything you know about life, then I bounce. Roxy hitting hard, feeling fucking sick. Half an hour just to balance it out. We be backing out, we be blacking out. All I fucking leave her out, then we be getting out. Glasses up and finger when they grab it like a grouse. We be loving out. And naughty is cracking up, you can let the curtains down now. Yeah. I want up with Toro, ain't no tomorrow, Mr. Call from sick, I woke up in the gown house.
I just bought 10 Roxy's, call a body dinner. Chronic place with something, I'm like, fuck it, let me. Rolling down your block, it ain't shit for the center. Told that bitch get out my ear, she need a chillin'. Xanax bars up in my drink before I pour 'em. We never fuck with you, fuck boy, don't act like you can. Take that motherfucking bed upside your skull. So full of them drugs, I might throw up, I knew I shouldn't.
Pull up with the motherfucking AK, talk this boy, good luck, young play, got the play forget my life is suicide.
Hold a thumb in front of your face. I'm serious, do it. Hold your thumb out in front of your face. Now close one eye. Now switch which eye is open. What do you see happen to the position of your thumb relative to the background? It should appear to move. With your right eye open, your thumb should appear over here. With your left eye open, the thumb will appear to be over here.
One jungle.
Move your thumb further away from your face. It will appear to move less against the background. This effect is called parallax and can also explain why, when you're driving along a road, the cars in the field nearby seem to be moving away at a higher speed than the distant hills. Stellar parallax can be used to measure the distance to nearby stars. It works in exactly the same way as the little experiment you just did with your thumb. Your thumb represents the star you are measuring, and the background wall is replaced with the background of very distant stars. If we move our viewing position, the star should appear relative to the distant stars. The closer the star is to us, the more it should appear to move. But how can we shift our viewing position?
Nice, молодцы, всё,
We don't need
ГГ.
to. The Earth is orbiting
Нормально
the Sun,
сыграли.
so we simply need to take two photographs of the sky 6 months apart, for example January and July. This is when the Earth is at two extreme positions of the orbit around the Sun. And then compare the position of this star in the two photos. We can now use trigonometry to work out the distance of the star. The tan of theta is equal to the distance from the Earth to the Sun divided by the distance from the Sun to the star, that is, opposite over adjacent. The distance from the Sun to the star is much, much bigger than the distance between the Earth and the Sun. So we can use the trigonometric simplification that tan theta, for very small angles, is approximately equal to theta. Thus we can say that theta is proportional to 1 over the distance to the star. The parsec is a unit specifically created for this relationship. If we have a parallax angle, theta, of 1 arcsecond, where an arcsecond equals 1/3600th of a degree, this corresponds to a distance of 1 parsec. The word parsec is short for parallax of 1 arcsecond. This leaves us with the simple equation d in parsecs is equal to 1 divided by p in arcseconds, where d is the distance to the star and p is the angle. Our nearest star other than the Sun is Proxima Centauri. It is 1.3 parsecs away, which means that it has a tiny parallax angle of less than 1 arcsecond. This is barely perceptible. With modern techniques, we can measure the distance to stars up to around 100 parsecs away using the parallax method. Note that even though the parsec unit is derived from the parallax method, it can still be used to express distances to objects that are far too far away for the parallax method to actually apply. Let's finish with a quick example. A star has a parallax angle P of 0.02 arcseconds. How far away is it? Well, simply d equals 1 divided by p. So 1 divided by 0.02 gives us 50 parsecs. Easy.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Cheap ways to secure your browsing from hackers. 1. Use NordVPN. 2. Get a tinfoil hat. 3. Live under a rock with no internet. You know what? Better.
How can we tell which of these street lamps is further away? The obvious answer is that the dimmer lamps are more distant, but what assumptions did we have to make? Well, we assume here that all of the lamps are giving out the same amount of light in the first place. A similar method can be used to determine the distance to stars. If we assume that all of the stars have the same power output, then comparing their brightness will tell us how far away they are. Unfortunately, not all stars do have the same power output. Larger or hotter stars will emit more radiation per second than smaller or cooler stars. The total power emitted by a star is known as its luminosity. This is measured in watts. The intensity of the light from the star as measured on Earth is known as its apparent brightness, and this is measured in watts per square metre. You may already be familiar with the equation relating intensity and power. That is, intensity equals power divided by surface area. We can replace I and P with apparent brightness B and luminosity L respectively to give us B brightness equals L luminosity divided by A surface area. But what is this area? When light is emitted from a star, it travels in all directions, spreading out as it does so. It is like an inflating sphere of light, where the power is being spread across the surface area of that sphere. So the area in our equation is the surface area of a sphere with a radius equal to the distance from the star. So this gives us our final equation. Brightness equals luminosity divided by 4 pi multiplied by the distance to the star squared. 4 pi r squared, of course, is the surface area of a sphere. So 4 pi d squared gives us the surface area of a sphere where the radius is the distance between the star and the observer. For example, Betelgeuse has an apparent brightness B equal to 2.0 times 10 to the power of -7 watts per square metre. It is 4.0 times 10 to the power of 18 metres away. What is Betelgeuse's luminosity? So L equals B multiplied by 4 pi d squared. So we substitute the numbers in. 2.0 multiplied by 10 to the power of -7 multiplied by 4 pi multiplied by 4.0 times 10 to the power of 18 all squared gives us a luminosity of 4.02 times 10 to the power of 31 watts. That's the power output of Betelgeuse.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Hi, in this video I'll be summarising the various astronomical objects that can be found in the universe. Planets are approximately spherical objects that directly orbit a star and that have cleared the orbital path that they follow of any other debris. There are 8 planets in the solar system. In recent years, we've discovered more than 2,000 exoplanets that orbit other stars in our galaxy. A moon is an object that orbits a planet. Comets are mixtures of ice and rock that have very long elliptical orbits around the Sun. Their tail always faces away from the sun, regardless of which direction they're moving in. Stars, such as our sun, are large balls of gas that emit vast amounts of energy into space. This energy is a result of nuclear fusion that is turning hydrogen into helium. In nuclear fusion, mass is converted into energy according to Einstein's famous equation E equals mc squared. This means that our sun is losing around 4 billion kilograms of mass every second. All stars are in hydrostatic equilibrium. This means that they hold their shape because the forces acting on them are balanced. The outward gas pressure caused by the high temperature hydrogen and helium is balanced by the gravitational force of the hydrogen and helium atoms acting upon each other. Some stars exist in binary systems with another star. Their mutual gravitational attraction causes the two stars to orbit a common central point. A planetary system is a group of objects orbiting a star, or indeed a binary star system, due to gravitational attraction. We call our planetary system the solar system. A constellation is a pattern of stars that appear close together when viewed from Earth, although they are not necessarily close to each other in space. Stellar clusters are groups of stars. Open clusters contain around 1,000 younger stars, whereas globular clusters contain up to around 100,000 much older stars. Nebulae are clouds of dust and gas. They're mainly made of hydrogen and helium. This is the Crab Nebula. Galaxies are enormous collections of stars. They rotate in space because all of the stars are orbiting a central point. Our own galaxy, the Milky Way, is 100,000 light years across and contains around 100 billion stars. Each of these stars may have their own planetary system. Some galaxies are grouped together into clusters or superclusters that spread across the universe. In between stars in a galaxy, and in between the galaxies, there is almost nothing, essentially a vacuum. Collectively, everything I've described in this video makes up the universe.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Helmaco. Välj mellan 1 eller 2 kött. Nu på McDonald's.
Hi, in this video I will introduce you to the 3 units of distance that we use when studying astrophysics. First, the astronomical unit. This is simply the mean distance between the Earth and the Sun. That's 1.50 times 10 to the power of 11 meters.
Oh my god.
The astronomical unit is useful for presenting distances within the solar system, but for distances elsewhere in the galaxy, or even the universe, it is far, far too small to be useful. The second unit you need to know is the light year. This is a unit of distance, not a unit of time. It's the distance travelled by light in a vacuum in 1 year. So that's 9.46 multiplied by 10 to the power of 50 meters. It's useful for measuring distance within our galaxy or across the universe. Our nearest star after the Sun, Proxima Centauri, is about 4 light years away. The photons of light we see from that star have taken 4 years to reach your eye. The light from the most distant observable objects in the universe began their journey 13 billion years ago, when the universe was in its infancy. When we look at the night sky, we are quite literally looking back in time. Finally, we have a unit most famous for being misused in Star Wars, the parsec. Despite what Han Solo said, it is a unit of distance and not time. It is defined as the distance that produces a parallax angle of 1 arcsecond. More about that in another video. Parsec is equivalent to about 3.3 light years, so it's mainly used for measurements within the galaxy. For intergalactic measurements, the megaparsec, 1 million parsec, is commonly used.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Förnya din uteplats med fantastiska erbjudanden från Jysk. Spara 20-50% på alla trädgårdsvaror. Till exempel en hopfällbar solstol med nackkudde för endast 275 kronor. Spara 45%. Eller...
Hi. In previous videos, I described how the parallax and brightness methods can be used to determine the distance to a star. However, the parallax method is only useful for nearby stars, and the brightness method has a serious limitation. How can we know if a star is large and far away, or small and nearby? In order to deduce the distance to other galaxies, we need a standard candle in that galaxy. That is, a star of known luminosity against which we can compare the other stars. Cepheid variable stars provide this. A Cepheid variable star expands and contracts in a predictable rhythm, causing measurable periodic variations in its luminosity. The period of this fluctuation happens to be proportional to the luminosity of the star. In other words, Cepheid variable stars that are emitting more power fluctuate more slowly, they have longer time periods. This means that we can measure the period of the fluctuation in the Cepheid variable star's brightness on Earth and use this to determine the luminosity of the star. Now that we have the luminosity and the brightness, we can use the inverse square law to determine the distance to the star.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Hi, in this video I'll be explaining what we can learn about stars without ever visiting them. The stellar spectrum of a star provides a series of clues that tell us a surprising amount. In my video, Emission and Absorption Line Spectra, I explained how line spectra are formed. In summary, absorption line spectra are the result of gases in a star's atmosphere, you can see it here during a solar eclipse, absorbing certain frequencies of radiation. As these photons are absorbed, they excite electrons to move to a higher energy level. These electrons then relax back to their ground state and they release a photon as they do so. This released photon may travel in any direction, not necessarily the same direction the original photon was travelling in, which results in certain wavelengths of light not reaching us. These wavelengths show up in the absorption line spectrum as dark lines. The lines represent unique fingerprints of the elements that are present in that star's atmosphere. So this technique led to the discovery of helium in the Sun more than a decade before it was discovered on Earth, hence it is named after Helios, the Greek god of the sun. Physicists can categorize stars based on their chemical composition by comparing their absorption spectra, i.e. looking for certain chemical fingerprints within the absorption spectra. Because these patterns are consistent within a spectral class, within a certain type of star, if we see that a star has a pattern that is shifted towards the red end of the spectrum, redshift, that means we can apply the Doppler effect to deduce that it is moving away from us. Likewise, if the spectral pattern is blue shifted, we can deduce that the star is moving towards us. But that's not all. Our spectral analysis can tell us even more. Using Wien's law, the peak wavelength of light received from a star can be used to determine the star's surface temperature. If we know the distance to the star, we can use the apparent brightness to work out its luminosity using the inverse square relationship. And finally, using that luminosity and the surface temperature, we can apply the Stefan-Boltzmann law to determine the star's surface area and therefore its size. So as you can see, studying a star's spectrum from many light years away can tell us an awful lot about the properties, the size of that star.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Bildkalibrera TV:n inför fotbollsfesten på...
Hi, in this video I'm going to explain the key features of the Hertzsprung-Russell diagram. This chart was first created about 100 years ago by two astronomers called Hertzsprung and Russell. The y-axis is a logarithmic scale of luminosity, where the power output of our sun is defined as a luminosity of L equals 1, and the scale then increases logarithmically, with the most powerful stars towards the top of the diagram and the least powerful stars towards the bottom of the diagram. The x-axis describes the temperature of the star, but the axis is reversed, with the hottest stars here about 30,000 Kelvin towards the left, and the cooler stars towards the right. Streaking across the middle of our diagram, we have the main sequence. This is the most populous group of stars. Our sun, by definition, sits somewhere in the middle of the diagram. All stars in the main sequence are stable and undergoing nuclear fusion to turn hydrogen into helium. These are middle-aged stars. Towards the right of the diagram, we have the red giants. They form from low or intermediate mass stars after the hydrogen in their core has been exhausted. Although they are cooler than the main sequence stars, they have a higher luminosity than many of them because they are so much larger. When a red giant exhausts its fuel, it sheds its outer layer and leaves behind a hot core as a white dwarf. The white dwarfs appear in the bottom left of the Hertzsprung diagram because, despite their high temperature, their small size means they have a low luminosity. Red supergiants are found above the red giants. They are relatively cool but are quite enormous. Their radius can be up to 1,000 times greater than our sun. Red supergiants form from very large main sequence stars. In the gap between
why would you smoke for them?
Red giants,
They are supposed to
and the
smoke
main
this
sequence,
one.
we have what is known as the instability strip.
By the way,
This strip contains several classes of variable stars,
Turkish.
including Cepheid variable stars. Finally, we can add diagonal lines to our Hertzsprung-Russell diagram. These are lines of constant radius, so allow us to give us some sort of sense of scale. For stars on the main sequence, there is a correlation between their mass and their luminosity. The higher the mass of a star, the more power it will emit. This makes sense, but the exact relationship is that the luminosity L is proportional to the mass raised to the power of 3.5. For example, if star B is twice the mass of star A, how many times bigger will its luminosity be? Well, its luminosity will be 11.3 times the luminosity of star A.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Cheap ways to secure your browsing from hackers. 1. Use NordVPN. 2. Get a tinfoil hat. 3. Live under a rock with no internet. You know what? Better stick to NordVPN.
Hi, in this video I will describe stellar evolution, that is how a star changes as its life comes to an end. First, let's consider a star with a mass no more than 4 times that of the Sun. In the core of a main sequence star, hydrogen is fusing into helium, releasing energy as it does so.
Why do you want to hear my voice?
When hydrogen in the core runs out, fusion will stop, and there will no longer be any gas pressure available to prevent the star from collapsing. This sudden collapse will increase the core's temperature so much that helium fusion can take place, producing heavier elements such as carbon, oxygen, silicon, and iron. The energy generated from this new round of nuclear fusion will cause the star to expand massively. Although it is generating more power than previously, this is spread over a much bigger area, so the surface temperature is lower, producing red light. The star is now a red giant. This will happen to our Sun in about 5 billion years. When it does, it will engulf Mercury and Venus, and it will almost reach the surface of the Earth. Whatever life forms may still be around by that point will be finally extinguished, which is a cheery thought. What happens next in the evolution of a small or medium-sized star like our Sun? A red giant will fuse heavier and heavier elements until it reaches iron. Iron has got one of the highest binding energies per nucleon. If you want to fuse it into heavier elements, you have to put in more energy than the reaction will release. The red giant cannot provide this, so fusion stops again, and once more, a lack of outward gas pressure will cause the star to collapse. The tenuous, relatively cool outer gas of the star will drift into space as a planetary nebula. Note that planetary nebulae are nothing to do with planets, it's an erroneous historical name that's stuck. If the remaining core of the star has a mass no more than 1.4 times the mass of the Sun, and this corresponds to an original star with a mass less than 4 times that of the Sun, it will become a white dwarf. This limit is known as the Chandrasekhar limit, and is because below this limit, the electron degeneracy pressure prevents further star collapse. The white dwarf is very hot, hence its colour, but it is no longer fusing. It will slowly fade for eternity like the dying embers of a fire until eventually it becomes invisible. But what happens to larger stars? Stars with a remnant mass above the Chandrasekhar limit, or the original mass that's more than 4 times the mass of the Sun. Well, their evolution is slightly different. Similar to low-mass stars, their core will collapse and they'll begin fusing heavier elements, but they'll expand into much larger stars called red supergiants. These can be up to 1,000 times the diameter of the Sun. When a red giant finally runs out of fusible material, it will also collapse, but the energy available in this collapse will be so great that even the electron degeneracy pressure of the core cannot prevent further collapse. This causes a supernova, an enormous release of energy which can briefly outshine the 100 billion other stars in the galaxy. A supernova is hot enough to fuse iron into even heavier elements. The fact that these elements are found in our bodies and on the Earth mean that we are made of the remnants of a supernova that happened somewhere in this region of the universe long before the formation of our Sun and the planets. We are quite literally made of stardust. Unless the original star was exceptionally massive, the remnants of the supernova will form a neutron star. A neutron star has collapsed to such an extent that all of the empty space from the atoms has been squeezed out, leaving only the nucleons behind. The density of a neutron star is tremendous. 1 teaspoon of neutron star material has got roughly the same mass as the combined mass of every human on Earth. The neutron star is prevented from collapsing any further by the neutron degeneracy pressure. However, if the star's remnant is more than around 2 to 3 solar masses, even this neutron degeneracy pressure is not enough to prevent total collapse. Stars above this limit, which is called the Oppenheimer-Volkoff limit, will collapse into black holes. The density of a black hole is so high that it has gravitational effects that prevent even light from escaping. Okay, let's summarise this journey. A low-mass star, that is one below the Chandrasekhar limit, will continue to fuse hydrogen into helium until it's run out of hydrogen. At that point, it will collapse, and then expand to form a red giant, where the core is hot enough to fuse helium into heavier elements, such as carbon and oxygen. Eventually, once the fusion process reaches iron, no more fusion can take place, so the core will collapse into a white dwarf, and the outer layers will gently drift off into space as planetary nebula. For high-mass stars, that is, those above the Chandrasekhar limit, they will expand to form red supergiants, and again, red supergiants will fuse helium into heavier elements all the way up to iron. Once they run out of fuel, they will collapse with so much energy that a supernova is triggered. Usually, a neutron star is left behind after this. This is an incredibly dense star that would collapse further if it wasn't for its neutron degeneracy pressure. However, for heavier remnants, those above the Oppenheimer-Volkoff limit, even the neutron degeneracy pressure is not enough to prevent further collapse, so the remnant collapses into a black hole. Finally, let's take a look at how these evolutionary paths would look on a Hertzsprung-Russell diagram. It's important to recognise that stars do not move along the main sequence. When they're on the main sequence, they have a fixed position. When a low-mass star becomes a red giant, it moves up and to the right, indicating that its power output is increasing but its temperature is decreasing. After shedding its outer layers as a planetary nebula, it moves around to the bottom left of the diagram, where the remaining core is very hot, but the star itself is small and relatively dim. Similarly, for a high mass star, which will start from higher up in the main sequence, it will move up and to the right to become a red supergiant. It will then move off the top of the chart as it becomes a supernova.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Alla var du vill! Alltid med fri frakt!
Hi, in this video I will discuss the evidence for the Big Bang model. When we analyse the light from almost all of the galaxies, we find that their stellar spectra are shifted towards the red end of the spectrum. They are red shifted. This tells us that these galaxies are moving away from us. I'll focus a little more on redshift in a later video. So the fact that all of the galaxies are moving away from us may lead us to the assumption that our galaxy must be at the centre of the universe, but that's not the case. You could measure from any point in the universe and all the other galaxies would appear to be moving away from you. If we take a look at this diagram, you can see 5 galaxies A, B, C, D and E before and after expansion. Note that the space in between every galaxy has increased from 1 unit to 2 units. If we take Galaxy A as our starting point, then the distance from Galaxy A to Galaxy C was 2 the first time, and is now 4. And the distance from Galaxy A to Galaxy D, where it was 3 before, is now 6. So if you were standing in Galaxy A, you may feel everything is moving away from you. You must be at the centre of the universe. So let's try from a different perspective. Let's imagine we were Galaxy D. Well, from Galaxy D's perspective, Galaxy B has moved from 2 units away to 4 units away. And Galaxy E has moved from 1 unit away to 2 units away. So from wherever you appear to be in the universe, in whichever direction you look, everywhere is expanding away from everything else. This is because space itself is expanding. The further the galaxy is from our vantage point, the faster it will appear to be receding from us, but more of that in my Hubble's law video. Since the universe is expanding, it follows that if we could reverse time, the universe would be getting smaller. At some point, therefore, all of space must have been condensed into a single point. The expansion of the universe, in terms of both space and time, from this point, is known as the Big Bang theory. A major piece of evidence for the Big Bang is the existence of cosmic microwave background radiation, or CMB. This was first predicted in 1948, although it wasn't discovered until it was accidentally picked up by a radio telescope in the 1960s. CMB radiation is electromagnetic radiation that permeates all of space in all directions. This means that it is isotropic. It has very low energy, equivalent to the radiation produced by a black body at 2.73 degrees above absolute zero, 2.73 Kelvin. There are 2 ways for us to understand the existence of CMB radiation, and both ways are perfectly valid. The first option is to consider that the universe began very, very hot, but has cooled down over the previous 14 billion years to an average temperature of 2.73 Kelvin. Therefore, the radiation that is emitted by the universe itself is equivalent to a black body at that temperature. Option 2 is to consider the stretching of waves. Sometime after the Big Bang, the universe became transparent and allowed electromagnetic radiation to pass through. This radiation from the Big Bang was obviously hot and therefore high frequency and short wavelength. As this radiation travelled through the universe itself continued to expand, causing the waves to be stretched until they reached the wavelength associated with a temperature of 2.73 Kelvin.
Thank you for watching this video from Cowan Physics. If you found it useful, please like, subscribe, and visit cowanphysics.com.
Hi, in this video I'll be introducing you to Hubble's law. In my previous video about the Big Bang, I explained that we know that the universe is expanding because all galaxies are receding away from us. This can be observed through the stellar spectra being redshifted. We can measure the distance to a galaxy using Cepheid variable stars. These two quantities can be plotted on a graph, producing an approximately linear relationship. Therefore, we can deduce that recessional velocity is proportional to distance. This is known as Hubble's law. The gradient of this line is known as the Hubble constant. Therefore, we can write the equation as v velocity is equal to the Hubble constant h0 multiplied by the distance d. The Hubble constant represents the current rate of expansion of the universe. It's important to recognise that the Hubble constant is not actually constant. It's only the current rate of expansion. We'll explore how this changes in a later video. The Hubble constant is the gradient of a velocity against distance graph. We know that distance divided by velocity equals time, so the Hubble constant must be 1 divided by time. We can check this by looking at the units. Typically, we use units of kilometers per second and megaparsecs on the graph, giving us a Hubble constant in kilometers per second per megaparsec. However, the SI units are, of course, meters per second and meters. So this would give us a Hubble constant with a unit of seconds to the -1 per second. Okay, so 1 divided by h0 will give us a time, but what does this time represent? This time represents how long it has taken for the galaxies to reach their current distance away from us, assuming that the expansion has been linear. In other words, it gives us an upper limit on the age of the universe. So the simplest equation in your data booklet, t approximately equals 1 divided by h0, actually gives us an estimate for something as profound as the age of the universe, which I think is quite cool. Here's an example. The current best estimate for the Hubble constant is around 70 kilometers per second per megaparsec. We can convert this to 70,000 meters per second per megaparsec. We know that 1 megaparsec is equal to 3.09 times 10 to the power of 22 meters. So in SI units, the Hubble constant will be 2.27 times 10 to the power of -18 seconds to the power of -1. Therefore, 1 divided by h0 will be equal to 4.41 times 10 to the power of 17 seconds, or 1.40 times 10 to the power of 10 years. That's about 14 billion years. This is a little higher than the current best estimate of the universe's age, of 13.8 billion years. This discrepancy is because the expansion of the universe is not linear.
Thank you for watching this video from Cowan Physics. If you found it useful, please like and subscribe, and visit cowanphysics.com.
Handla vad du vill. Alltid med fri frakt.
Hi, in this video I will explain how we can use redshift and the cosmic scale factor to make calculations about our expanding universe. The Doppler effect is the phenomenon we experience when a car moves past us. As the car approaches, we hear a higher frequency sound than when it is moving away. If we think of it in terms of the wavefront, we can imagine the car emitting a wavefront, then partially catching up with that wave before it emits the next wavefront. The effect is that the wavefronts are closer together than they should be when they reach our ear, so we hear a higher frequency sound. Likewise, when the car is moving away from us, the effect is reversed and we hear a lower frequency sound because the waves are further apart than they should be. The Doppler effect also occurs with light. When a source of light is moving towards us, its light is shifted towards the blue end of the spectrum because it has a higher frequency, and when it is moving away from us, it is shifted towards the red end because it has a lower frequency. This is called redshift. A measurement of this redshift can tell us how fast a galaxy is receding away from us. If you have previously studied the Doppler effect, you'll be aware that for electromagnetic radiation, as long as c, the speed of light, is much, much greater than v, the recessional speed of the moving galaxy, the redshift can be approximated with z, the redshift, is equal to delta lambda divided by lambda 0, which is approximately equal to v divided by c, where delta lambda is the change in the wavelength of the observed light, and lambda 0 is the wavelength of emitted light, and v is the relative velocity of the light source, and of course c is the speed of light in a vacuum. For example, the absorption line in a line spectra corresponding to helium has a wavelength of 468.6 nanometers. But this is observed at 499.3 nanometers. What is the recessional speed of this star? So we can calculate z equals the change in wavelength divided by the original wavelength, which is going to be 499.3 minus 468.6 divided by 468.6. And that gives us a redshift of 6.55 times 10 to the negative 2. Notice there is no unit for redshift, it is a ratio. So to determine v, that is the recessional velocity, we multiply the redshift, 6.55 times 10 to the minus 2, by
I'm Dave again, here with another question bank question in astrophysics.
This is the first video for the IB Astrophysics op.
The sun is a star. That's a profound statement, and one that's not really all that obvious. Those little sparks in the night sky are pretty, but don't look anything at all like the hot, blazing orb that lights up our days. It was a pretty remarkable intellectual leap to understand the sun and the stars are just different flavors of the same kind of object. The only difference is that the sun is close, but the stars are terribly far away, so they're fainter. Right away, let's clear up a misconception. A lot of people say the sun is a middle-sized average star, but that's not fair. Sure, it's somewhere in the middle of the size range of stars, but the vast majority of stars are dim red dwarfs, far smaller than the sun. By size and number, the sun ranks in the top 10% of stars in the galaxy. In our solar system, it's clearly the dominant object, brighter, more massive, and more influential than anything else. But what is it? The sun is essentially a big hot ball of mostly hydrogen gas. It's 1.4 million kilometers across, more than 100 times the Earth's diameter, and big enough that well over 1 million Earths could fit inside of it. And it's massive, 300,000 times more massive than the Earth, a staggering 2 octillion tons of gas. But if we want to truly understand the sun, we have to look into its heart. At the very core of the sun, conditions are hellish. The pressure is a crushing 260 billion times the Earth's atmospheric pressure, and it's a searing 15 million degrees Celsius. Under those conditions, hydrogen is completely ionized, which means the electrons in the atoms are stripped from their protons. This makes the core a thick soup of ultra-hot subatomic particles. In fact, the protons are squeezed together so hard by the octillions of tons of mass lying on top of them that an amazing thing happens. They fuse together. Through a complicated series of steps, the hydrogen atoms fuse together to form the heavier element helium. Along the way, some of the nuclear energy stored in those atoms is released. That amount of energy is described by Einstein's famous equation E equals mc squared, which states that mass can be converted into energy and vice versa. Atoms are pretty small though, so each helium atom made in the sun's core generates only a tiny bit of energy, but a lot of helium atoms are made. A lot. Get this. Every second of every day, the The sun converts 700 million tons of hydrogen into 695 million tons of helium. The missing 5 million tons, the equivalent weight of 15 Empire State Buildings, is converted into energy. And that's a lot of energy. Enough, in fact, to power a star. It's equivalent to detonating 400 billion 1 megaton nuclear bombs every single second. That's millions of times the entire nuclear arsenal of our planet, every second. And that's why, even from a distance of 150 million kilometers, the sun is so bright you can't even look at it. Even from that distance, its heat can be felt on your skin when you stand outside. Hydrogen fusion occurs in the core of the sun. The energy released heats the gas above the core, but not quite enough to fuse hydrogen into helium. Further from the sun's center, the gas becomes less dense, and at some point, the heat pouring up from below makes the gas buoyant. It rises in the same way a hot air balloon on Earth rises. This process is called convection, and it's an efficient way of transferring heat. Huge columns of rising hot gas stretch hundreds of thousands of kilometers high, bringing the sun's internal heat to the surface. The gas then cools and sinks back down into the interior. We can actually see the tops of these columns packed together across the sun's face. Above the convecting layer is a much thinner, cooler layer very near the sun's surface called the photosphere, or literally the sphere of light. This is where the density of the material inside the sun gets thin enough that it becomes transparent. Light can shine right through it. At this point, the energy from inside the sun is free to travel into space. It's this light that we see when we look at the sun. The sun is a gas and doesn't have a solid surface, but the gas in the photosphere thins so rapidly compared to the sun's huge size that you can think of it as the sun's surface. And there's one final layer above that, the ethereally thin corona, sort of like the sun's atmosphere. It's less than 1% as dense as the photosphere, but actually much hotter. Temperatures there can reach over 1,000,000 degrees. However, it's so thinly dispersed that it's incredibly faint and can only be seen during a total eclipse or using special telescopes that block the intense light from the sun itself. The corona extends for millions of kilometers. And in a sense, it doesn't actually end. The corona merges into what's called the solar wind, a stream of subatomic particles moving away from the sun. It blows out in all directions, though mostly along the sun's equator. The speed of the wind is usually well over 1,000,000 kilometers per hour. Yes, seriously, and can reach speeds even much higher than that. When hydrogen fuses into helium in the sun's core, the energy is released in the form of light. This light immediately smacks into a subatomic particle, which absorbs it, converts a little bit of the energy into motion, and re-emits the light with a little bit less energy. The light works its way out of the sun this way, losing energy every time it encounters a particle, until eventually it gets to the surface and is free to fly away into the universe as a much lower energy photon of visible light. So how long does this process take? I've seen different numbers for it, some as much as 1,000,000 years. But a lot of those calculations don't model conditions inside the sun accurately. For example, they don't take into account the gas convecting for hundreds of thousands of kilometers. More modern calculations show that it takes closer to 100,000 or 200,000 years for the energy to work its way out. That's still a pretty long time. The light you see from the sun now got its start in the sun's core around the time Homo sapiens first appeared in Africa. The sun's surface is, to put it kindly, a mess. And the key to that mess is magnetism. I've been saying the sun is made of gas, but that's not entirely accurate. It's so hot inside the sun that electrons are stripped from their parent atoms in the gas, creating what's called a plasma, a gaseous soup of charged particles. We'll learn more about that in a later episode. But what's important now is the fact that a moving electric charge generates a magnetic field. The interior of the sun is essentially all charged particles in motion. Convection, coupled with the sun's rotation, sets up rivers or streams of plasma inside the sun, each generating and carrying its own magnetic field. When this plasma reaches the sun's surface, their magnetic fields do too. Maybe you've seen those looping arcs of magnetism around a bar magnet when it affects iron filings on a piece of paper. The solar magnetic fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even get tangled up. When the plasma reaches the surface, it cools. But if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe. Plasma shines because it's hot, but as it cools, it dims. It sits on the surface dimming, producing a dark spot on the surface of the sun, which we call a sunspot. Sunspots can be huge. They commonly dwarf the entire Earth, and some are so big they can be seen without using a telescope. as long as you're wearing adequate eye protection, of course. Around the edges of sunspots, the magnetic field lines are concentrated. This can energize the plasma even further, heating it up. This creates a bright rim around sunspots called faculae, Latin for little torch. The dark parts of sunspots dim the overall light from the sun, but faculae can be so intense they compensate for that and even add more light. Ironically, sunspots actually increase the energy output of the sun. Plasma on the sun's surface can flow along these magnetic loops too. This can create huge arcs of material called prominences or filaments, stretching for hundreds of thousands of kilometers across the sun, looking like fiery arches. We think these magnetic field lines are feeding energy from the sun's surface into the corona, which is why it's so much hotter. It's not exactly clear how this happens, but scientists are following several leads right now. This long-standing mystery may soon be solved. Magnetic fields on the sun also have a huge amount of energy stored in them. You can think of them like very tightly wound and very stiff springs. But remember, these magnetic field lines get tangled up. If conditions are right, they can actually snap, in essence creating a gigantic short circuit. When this happens, all that vast energy stored in the lines explodes outwards all at once in an event we call a solar flare. Even an average solar flare is mind-crushingly powerful. A big one can release as much as 10% of the entire sun energy output. This explosion blasts out high-energy light and launches material off the surface of the sun at high speeds, sending it into interplanetary space. Another type of solar eruption is called a coronal mass ejection, or CME. It's similar to a flare, but if a flare is like a tornado, intense and localized, a CME is like a hurricane, huge and strong. Like flares, they form when tangled magnetic field lines erupt, blasting out energy, but they occur higher off the sun's surface. Both flares and CMEs eject material into space. Billions of tons of it, in fact. This blast of debris can hit the Earth, and when it does, there can be profound effects. Our atmosphere absorbs the high-energy light, protecting us. Also, the subatomic particles are generally deflected by the Earth's magnetic field, so we're okay. But if conditions are right, the Earth's magnetic field can interact with the particles. Massive numbers are funneled down into Earth's atmosphere near the poles, causing the air to glow. This is what we call the aurora, or the northern and southern lights. Depending on the shape of the magnetic field, the auroras can form spectacular multicolored ribbons and sheets. Not all the effects are benign, though. As the magnetic fields interact, they can induce very strong currents of electricity in the Earth's crust. This can overload power grids, causing blackouts. In 1989, Quebec suffered a massive power outage from a solar storm. The very first such storm ever detected was in 1859, and it was also the most powerful ever seen. If an event like that were to happen today, it could cause worldwide blackouts and potentially be very damaging. Satellite electronics would be fried too, and we depend on those satellites for our modern civilization. In fact, in 2012, a huge storm, probably the equal of the 1859 event, blasted away from the sun in another direction, missing the Earth. Had it hit us, well, you probably wouldn't be watching this video now. We'd still be recovering. This is why studying the sun is so important. We depend on it for light and heat and the very basis of life itself, but it's entirely capable of knocking our society to its knees. Understanding it is critical to our future. The sun is the 2 octillion-ton gorilla in the room. We need to respect that. Today you learned that the sun is a star powered by nuclear fusion in its core. Hot plasma moves inside the sun, creating magnetic fields, which in turn can create sunspots, solar flares, and coronal mass ejections. These events can generate aurorae on Earth, cause power blackouts, and damage satellites. This episode is brought to you by Squarespace. The latest version of their platform, Squarespace 7, has a completely redesigned interface, integrations with Getty Images and Google Apps, new templates, and a new feature called Cover Pages. Try Squarespace at squarespace.com and enter the code CRASHCOURSE at checkout for a special offer. Squarespace, start here, go anywhere. Crash Course Astronomy is produced in association with PBS Digital Studios. Go to their channel and find lots more awesome videos. This episode was written by me, Phil Plait. The script was edited by Blake DiPastino, and our consultant is Dr. Michelle Thaler. It was co-directed by Nicholas Jenkins and Michael Aranda, edited by Nicole Sweeney, and the graphics team is Thought Cafe. Hey, Phil Plait here, and this is Crash Course Astronomy. In last week's episode, I mentioned that nearly all the information we have about the universe comes in the form of light. But how does that light get made? What can it tell us about these astronomical objects? And honestly, what is light? Here's a hint.
One diaphragm for mankind.
Light is a wave. It took centuries of thought and experiments to figure that out, and to also figure out that, at its most basic, light is a form of energy. It travels in waves, similar to waves of water in the ocean. Except with light, the things doing the waving are electric and magnetic fields. Literally, light is a self-contained little bundle of these two fields intertwined. That's why we call light electromagnetic radiation. The details of this are very complex, but we can make some pretty good overall observations about light just from thinking of it as a wave. If you're floating in the ocean, you'll move up as a wave passes you, then back down, then back up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a wave, it has a wavelength as well, and this may be its single most important feature. That's because the energy of light is tied to its wavelength. Light with a shorter wavelength has more energy, and light with a longer wavelength has less energy. And our eyes have a really convenient way of detecting these different energies. Color. What you think of as the color violet is actually light hitting your eye that has a short wavelength. Red light has a longer wavelength, about twice the distance between crests as violet light. All the colors in between, orange, yellow, green, blue, have intermediate wavelengths. This spread of colors, wavelengths, is called a spectrum. Over millions of years, our eyes have evolved to detect the kind of light the sun emits most strongly. Well, that makes sense. That makes it easier for us to see. We call this kind of light visible light. But that's just the narrowest sampling of all the different wavelengths light can have. If light has a slightly shorter wavelength than what our eyes can see, it's invisible to us, but it's still real. We call that ultraviolet light. Light with shorter wavelengths than that fall into the X-ray part of the spectrum, and light waves with the shortest wavelengths of all are called gamma rays. At the other end, light with slightly longer wavelengths than the reddest color we can see is called infrared light. Light waves longer than that are called microwaves, and those with the longest wavelengths of all are called radio waves. These different groups don't really have hard and fast definitions. Just think of them as general guidelines. But together, we call all of these different kinds of light the electromagnetic, or EM, spectrum. And remember, energy goes up when the wavelength gets shorter. So ultraviolet light has a higher energy than violet, X-rays have a higher energy than that, and gamma rays have the highest energy of all. Infrared light has lower energy than red light, microwaves lower than that, and radio waves have the lowest energy. When you look at the whole EM spectrum, you'll probably notice that we really do only see a teeny little sliver of it. Most of the universe is invisible to our eyes. That's why we build different kinds of telescopes, to detect the kind of light our eyes can't detect. They let us see a lot of stuff that otherwise we'd never notice. So you might be asking, how is light made? Well, one of the most basic properties of matter is that when you heat it up, it gains energy, and then it tries to get rid of that energy. Since light is energy, one way to get rid of energy is to emit light. Another important property of matter is that the kind of light an object emits depends on its temperature. An object that's hotter will emit light with a higher energy, that is, a shorter wavelength. Cooler objects give off light with a longer wavelength. You may have seen this in action. Heat up an iron bar and it starts to glow red, then orange, then yellow as it gets hotter. The color, the wavelength of light emitted, changes as the bar heats up. Astronomers use a shorthand for this. We say that light with a shorter wavelength is bluer and light with a longer wavelength is redder. Don't take this literally. We don't really mean more blue or more red, just that the wavelengths are decreasing or increasing. So in this lingo, ultraviolet light is bluer than blue and X-rays are bluer than ultraviolet. So objects that are more energetic, that have a higher temperature, are bluer than cooler, redder objects. This rule of thumb works really well for dense objects like iron bars and stars. Even humans. You emit light, but it's in the far infrared, well beyond what our eyes can see. There are less dense objects in space too, like gas clouds, and the way they emit light is different. To understand that, we have to zoom in on them, way, way in, and look at their individual atoms. And to understand that, we need to take a brief diversion into atomic structure. Atoms are the building blocks of matter. In general, atoms are made up of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive electric charge, electrons a negative charge, and neutrons are neutral. Protons and neutrons are much more massive than electrons and occupy the centers of atoms in what's called the nucleus. Electrons whiz around the nucleus, their negative charge attracted by the proton's positive charge. The type of atom depends on how many protons it has in the nucleus. Hydrogen has 1 proton, helium 2, lithium 3, and so on up the periodic table of elements. It's common to think of the electron as orbiting the nucleus, like a planet orbits the sun. But that's not really the case. The real situation is fiendishly complex and involves pretty hairy quantum mechanics. But in the end, the electron is only allowed to occupy very specific volumes of space around the nucleus, and those depend on the electron's energy. Think of these like stairs on a staircase, where the landing is the nucleus. When you walk up the stairs, you have to use energy to go up, and when you do, you have to go up a whole step at a time. If you don't have the energy to get to the next step, you can't move. You can be on the first step or the second step, but you can't be on the first and a half step. There isn't one. Electrons are the same way. They whiz around the nucleus with a very discrete amount of energy. If you give them an additional precise amount of energy, they'll move up to the next energy level, the next step. But if you give them the wrong amount, they'll just sit there. The opposite is true as well. Electrons can be in a higher energy state, up on a higher step, and then give off energy when they jump down. The amount they give off is exactly the same amount needed to get them to jump up in the first place. How do they get this energy? Light. If light hitting the atom has just the right amount of energy, the electron will absorb it and jump up. It can also jump down and emit light at that energy too. An electron can also jump 2 steps or 3 or whatever, but it needs exactly the right energy to do it. But as I said earlier, energy and wavelength are the same thing, and that's equivalent to color. So when an electron jumps up or down, it absorbs or emits a very specific color of
Damn. Hello.
Ja, du är HSR på där. Jag tror jag borde nog hålla käften. Jag pratar väldigt mycket.
of light. Not only that, but the steps are different for different atoms. To stick with our analogy, it's like different atoms are different staircases with different heights between the steps. So, when an electron jumps down a step in a hydrogen atom, it emits a different energy, a different color of light, than an electron jumping down in a helium or calcium atom. And this is the key to the universe. Because different atoms emit different colors of light. If we can measure that light, in principle, we can determine what an object is made of, even if we can't touch it, even if it's a bazillion light years away. And we can. Can you tell the difference between these two squares? They're a very slightly different shade of red. Your eye probably can't tell the difference, but a spectrometer can. This is a device that can precisely measure the wavelength of light and can, for example, distinguish light emitted by a hydrogen atom from light emitted by helium. When you hook one of these spectrometers up to a telescope, you can figure out what astronomical objects are made of. In the case of thin gas clouds in space, the atoms are basically floating free, rarely bumping into one another. The atoms emit those individual colors of light, allowing us to identify them. Unlike dense stars, the color of the thinner gas depends more on what's in it than its temperature. And this is how we learned what the universe is made of. Stars and gas clouds in space are mostly hydrogen, with some helium and heavier elements thrown in. Jupiter has methane in its atmosphere, Venus carbon dioxide. Everything in the universe has its own mix of ingredients, like cakes at a bakery. With spectroscopy, we can taste them. But wait, there's more. You're probably familiar with the Doppler effect, the change in pitch when, say, a motorcycle goes by. In sound, the wavelength defines the pitch. Higher tones have shorter wavelengths, and lower tones, longer wavelengths. When the motorcycle is headed toward you, the sound waves get compressed, causing the pitch to rise. After it passes you, the pitch drops because the wavelengths get stretched out. The same thing happens with light. If an object is headed toward you, the wavelength of light from the source gets compressed, shorter. We say the light is blue shifted. If it heads away, the wavelength gets longer and it's red shifted. Apply that to a spectrum, and by measuring that shift, we can tell if an object is moving toward or away from us. Here's a teaser. This becomes super important later when we talk about galaxies. Spoiler alert, the universe is expanding, and it's this redshift that allowed us to figure that out. And that's still not the end of it. With other spectroscopic techniques, we can determine if an object is spinning and how fast, whether it has a magnetic field and how strong it is, and even how massive and dense an object is. A vast amount of the fundamental properties of astronomical objects can be found just by dissecting their light into individual colors. Almost everything we know about the universe comes from the light objects in it give off. Pictures of astronomical objects show us their structure, their beauty, and hint at their history. But with spectra, we can examine their blueprints. Today, you learned that light is a form of energy. Its wavelength tells us its energy and color. Spectroscopy allows us to analyze those colors and determine an object's temperature, density, spin, motion, and chemical composition. Crash Course Astronomy is produced in association with PBS Digital Studios. Head over to their channel for even more awesome videos. This episode was written by me, Phil Plait. The script was edited by Blake T. Pastino, and our consultant is Dr. Michelle Thaler. It was directed by Nicholas Jenkins. The script supervisor and editor is Nicole Sweeney. The sound designer was Michael Aranda, and the graphics team is Thought Cafe.
Mina bästa vänner.
Nice.
Nej då.
Jag ska fritera till friterad kyckling.
Jag ringer maffian. Vad gör du? Vad gör du? Vad gör du? Är du? Nej, det är rasist. Jag gör rasist. Bitch ass up. Rasist. Hallå, flytta.
Oh, hey, sorry, I don't mean to be rude. I'm just trying to figure out how far away my thumb is. How? Parallax. Centuries ago, people thought the stars were holes in a huge crystal sphere letting through heavenly light. It wasn't clear just how big the sphere was, but it was pretty dang big. I have some sympathy for them. By eye, and for all intents and purposes, the stars are infinitely far away. If you drive down a road, you'll see nearby trees flying past you, but distant mountains move more slowly. The moon is so far, it doesn't seem to move at all compared to nearby objects. And it's easy for your brain to think it's much closer, smaller, and actually following you, which is a bit creepy. Sometimes people even think it's a UFO tailing them. Finding the distance to something really far away is tough. It's not like you can just pace off the distance. Or can you? The ancient Greeks knew the Earth was round, and there are lots of ways to figure that out. For example, ships sailing over the horizon seem to disappear from the bottom up, as you'd expect as they slip around the Earth's curve. But how big is the Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes figured it out. He knew that at the summer solstice, the sun shone directly down a well in the city of Syene at noon. He also knew that at the same time, it was not shining straight down in Alexandria and could measure that angle. There's a legend that he paid someone to pace off the distance between the two cities so he could find the distance between them. But more likely, he just used the numbers found by earlier surveying missions. Either way, knowing the distance and the angle, and applying a little geometry, he calculated the circumference of the Earth. His result, a little over 40,000 kilometers, is actually amazingly accurate. For the very first time, humans had determined a scale to the universe. That first step has since led to a much, much longer journey. Once you know how big the Earth is, other distances can be found. For example, when there's a lunar eclipse, the shadow of the Earth is cast on the moon. You can see the curve of the Earth's edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry, you can figure out how far away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part. His methods were sound, and they were used later by great thinkers like Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over 1,000 years before the invention of the telescope. And I think it also says a lot that these ancient thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton, laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name, the Astronomical Unit, or AU. Mind you, not an astronomical unit, the one. That's how fundamental it is to understanding everything. A lot of methods were attempted. Sometimes Mercury and Venus transit or cross the face of the Sun. Timing these events accurately could then be used to plug numbers into the orbital equations and get the length of an AU. Grand expeditions were sent across the globe multiple times to measure the transits and didn't do too badly. But our atmosphere blurs the images of the planets, putting pretty big error bars on the timing measurements. The best they could do was to say the AU was 148,510,000 kilometers, plus or minus 800,000 kilometers. That's good, but not quite good enough to make astronomers happy. Finally, in the 1960s, astronomers used radio telescopes to bounce radar pulses off of Venus. Since we know the speed of light extremely accurately, the amount of time it takes for the light to get to Venus and back could be measured with amazing precision. Finally, after all these centuries, the astronomical unit was nailed down. It's now defined to be 149,597,870.7 kilometers. So there. The Earth orbits the Sun on an ellipse, so think of that as the average distance of the Earth from the Sun. Knowing this number unlocked the solar system. It's the fundamental meter stick of astronomy and the scale we use to measure everything. Having this number meant we could predict the motions of the planets, moons, comets, and asteroids. Plus, it meant we could launch our probes into space and explore these strange new worlds for ourselves, see them up close, and truly understand the nature of the solar system. And it's even better than that. Knowing the astronomical unit meant unlocking the stars. We have 2 eyes, and this gives us binocular vision. When you look at a nearby object, your left eye sees it at a slightly different angle than your right eye. Your brain puts these 2 images together, compares them, does the geometry, and gives you a sense of distance to that object. And you thought your teacher lied when she said math was useful in everyday life. We call this ability depth perception. You can see it for yourself by doing the thumb thing. As you blink one eye and then the other, your thumb appears to shift position relative to more distant objects. That shift is called parallax. The amount of shift depends on how far apart your eyes are and how far away the object is. If you know the distance between your eyes, we'll call this the baseline. Then you can apply some trigonometry and figure out how far away the object is. If the object is nearby, it shifts a lot. If it's farther away, it shifts less. It works pretty well, but it does put a limit on how far away we can reasonably sense distance with just our eyes. Stars are a bit beyond that limit. If we want to measure their distance using parallax, we need a lot bigger baseline than the few centimeters between our eyes. Once astronomers figured out that the Earth went around the Sun rather than vice versa, they realized that the Earth's orbit made a huge baseline. If we observe a star when the Earth is at one spot, then wait 6 months for the Earth to go around the Sun to the opposite side of its orbit and observe the star again, then in principle we can determine the distance to the star assuming we know the size of the Earth's orbit. That's why knowing the length of the astronomical unit is so important. The diameter of Earth's orbit is about 300 million kilometers, which makes for a tremendous baseline. Hooray! Except, oops, when stars were observed, no parallax was seen. Was Helios edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry, you can figure out how far away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and Sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the Sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part. His methods were sound, and they were used later by great thinkers like Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over 1,000 years before the invention of the telescope. And I think it also says a lot that these ancient thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name, the astronomical. Twinkle, twinkle, little star. Oh, I know who you are. At first glance, stars pretty much all look alike. Twinkly dots scattered across the sky. But as I talked about in episode 2, when you look more closely, you see differences. The most obvious is that some look bright and some faint. As I said then, sometimes that's due to them being at different distances, but it's also true that stars emit different amounts of light too. If you look through binoculars or take pictures of them, you'll see that they're all different colors too. Some appear white, some red, orange, blue, and for a long time, the reason for this was a mystery. In the waning years of the 19th century, astrophotography was becoming an important scientific tool. Being able to hook a camera up to a telescope and take long exposures meant being able to see fainter objects, revealing previously hidden details. It also meant that spectroscopy became a force. Say it with me now. For science! A spectrum is the result when you divide the incoming light from an object into individual colors or wavelengths. This reveals a vast amount of physical data about the object, but in the late 1800s, we were only just starting to figure that out. Interpreting stellar spectra was a tough problem. The spectrum we measure from a star is a combination of 2 different kinds of spectra. Stars are hot, dense balls of gas, so they give off a continuous spectrum. That is, they emit light at all wavelengths. However, stars also have atmospheres, thinner layers of gas above the denser inner layers. These gases absorb light at specific wavelengths from the light below, depending on the elements in them. The result is that the continuous spectrum of a star has gaps in it, darker bands where different elements absorb different colors. At first, stars were classified by the strengths of their hydrogen lines. The strongest were called A stars, the next strongest B, then C, and so on. But in 1901, a new system was introduced by spectroscopist Annie Jump Cannon, who dropped or merged a few of the old classifications and then rearranged them into one that classified stars by the strengths and appearances of many different absorption lines in their spectrum. A few years later, physicist Max Planck solved a thorny problem in physics, showing how objects like stars give off light of different colors based on their temperature. Hotter stars put out more light at the blue end of the spectrum, while cooler ones peaked in the red. Around the same time, Bengali physicist Meghnad Saha solved another tough problem: how atoms give off light at different temperatures. 2 decades later, the brilliant astronomer Cecilia Payne-Gaposchkin put all these pieces together. She showed that the spectra of stars depended on the temperatures and elements in their atmospheres. This unlocked the secrets of the stars, allowing astronomers to understand not just their composition, but also many other physical traits. For example, at the time it was thought that stars had roughly the same composition as the Earth. But Payne-Gaposchkin showed that stars were overwhelmingly composed of hydrogen, with helium as the second most abundant element. The classification scheme proposed by Cannon and decoded by Payne-Gaposchkin is still used today, and arranges stars by their temperature, assigning each a letter. Because they were rearranged from an older system, the letters aren't alphabetical. So the hottest are O-type stars, slightly cooler are B, followed by A, F, G, K, and M. It's a little weird, but many people use the mnemonic, "Oh be a fine guy, kiss me," or "Oh be a fine girl, kiss me," to remember it, which was dreamed up by Annie Jump Cannon herself. Each letter grouping is divided into 10 subgroups, again according to temperature. We've also discovered even cooler stars in the past few decades, and these are assigned the letters L, T, and Y. The Sun has a surface temperature of about 5,500 degrees Celsius and is a a G2 star. A slightly hotter star would be a G1, and a slightly cooler star a G3. Sirius, the brightest star in the night sky, is much hotter than the sun and is classified as an A0. Betelgeuse, which is red and cool, is an M2. Stars come in almost every color of the rainbow. Hot stars are blue, cool stars red. In between, there are orange and even some yellow stars. But there are no green stars. Look as much as you want, and you won't find any. It's because of the way our eyes see color. A star can put out lots of green light, but if it does, it'll also emit red, blue, and orange. And our eyes mix those together to form other colors. A star can actually emit more green light than any other color, but we'll wind up seeing it as white. How do I know? Because if you look at the sun's spectrum, it actually peaks in the green. Isn't that weird? The sun puts out more green light than any other color, but our eyes see all the mixed colors together as white. Wait, what? White? You may be thinking the sun is actually yellow. Not really. The light from the sun is white, but some of the shorter wavelengths like purple and blue and some green get scattered away by molecules of nitrogen in our air. Those appear to be coming from every direction but the sun, which is why the sky looks blue. The sun doesn't emit much purple, so the sky doesn't look purple, and the green doesn't scatter as well as blue. That gives the sun a yellowish tint to our eyes. And looking at the sun is painful anyway, so it's hard to accurately gauge what color it appears. That's also why sunsets look orange or red. You're looking through more air on the horizon to see the sun, so all the bluer light is scattered away. So we can use spectra to determine a lot about a star. But if you combine that with knowing a star's distance, things get amazing. You can measure how bright the star appears to be in your telescope, and by using the distance, you can calculate how much energy it's actually giving off, what astronomers call its luminosity. An intrinsically faint light looks bright if it's nearby, but so does a very luminous light far away. By knowing the distance, you can correct for that and figure out how luminous the objects actually are. This was, no exaggeration, the key to understanding stars. A lot of a star's physical characteristics are related. Its luminosity depends on its size and temperature. If two stars are the same size, but one is hotter, the hotter one will be more luminous. If two stars are the same temperature, but one is bigger, the bigger one will be more luminous. Knowing the temperature and distance means knowing the stars themselves. Still, it's a lot of data. A century ago, spectra were taken of hundreds of thousands of stars. How do you even start looking at all that? The best way to understand a large group of objects is to look for trends. Is there a relationship between color and distance? How about temperature and size? You compare and contrast them in as many ways possible and see what pops up. I'll spare you the work. A century ago, astronomers Einar Hertzsprung and Henry Norris Russell made a graph in which they plotted a star's luminosity versus its temperature. When they did, they got a surprise. A very strong trend. This is called an HR diagram, after Hertzsprung and Russell. It's not an exaggeration to call it the single most important graph in all of astronomy. In this graph, really bright stars are near the top, fainter ones near the bottom. Hot blue stars are on the left, and cool red stars on the right. The groups are pretty obvious. There's that thick line running diagonally down the middle, the clump to the upper right, and the smaller clump to the lower left. This took a long time to fully understand, but now we know this diagram is showing us how stars live their lives. Most stars fall into that thick line, and that's why astronomers call it the main sequence. The term is a little misleading. It's not really a sequence per se, but as usual in astronomy, it's an old term and we got stuck with it. The reason the main sequence is a broad, long line has to do with how stars make energy. Like the sun, stars generate energy by fusing hydrogen into helium in their cores. A star that fuses hydrogen faster will be hotter because it's making more energy. The rate of fusion depends on the pressure in a star's core. More massive stars can squeeze their cores harder, so they fuse faster and get hotter than low-mass stars. It's pretty much that simple, and that explains the main sequence. Stars spend most of their lives fusing hydrogen into helium, which is why the main sequence has most of the stars on it. Those are the ones merrily going about their starry business of making energy. Massive stars are hotter and more luminous, so they fall on the upper left of the main sequence. Stars with lower mass are cooler and redder, so they fall a little lower to the right, and so on. The sun is there too, more or less in the middle. What about the other groups? Well, the stars on the lower left are hot, blue-white, but very faint. That means they must be small, and we call them white dwarfs. They're the result of a star like the Sun eventually running out of hydrogen fuel. We'll get back to them in a future episode. The stars on the upper right are luminous but cool. They must therefore be huge. These are red giants, also part of the dying process of stars like the Sun. Above them are red supergiants, massive stars beginning their death stage. You can see some stars that are also that luminous, but at the upper left. Those are blue supergiants. They're more rare, but they too are the end stage for some stars. And again, we'll get to them soon enough in a future episode. But I'll just say here that it doesn't end well for them. But on a brighter note, we literally owe our existence to them. And this implies something very nifty about the HR diagram. Stars can change position on it. Not only that, but massive stars versus low mass stars age differently and go to different parts of the HR diagram as they die. In many ways, the diagram allows us to tell at a glance just what a star is doing with itself. This difference between the way low-mass stars like the Sun and higher-mass stars age is actually critical to understanding a lot more about what we see in the sky. So much so that they'll be handled separately in later episodes. I'm sorry to tease so much about what's to come, but this aspect of stars, finally understanding them physically, was a major step in astronomy, leading to understanding so much more. And don't you worry, we'll get to all that. Today you learned that stars can be categorized using their spectra. Together with their distance, this provides a wealth of information about them, including their luminosity, size, and temperature. The HR diagram plots stars' luminosity versus temperature, and most stars follow along the main.
Jag har bottarna för jag är sämst.
In sequence where they live most. The sky, we now know, is full of stars and planets. Stars are massive enough to fuse hydrogen.
Ja, det finns kit.
Fucking just defuse, man. You don't need defuse kit.
I didn't.
Why
have a
are you
defuse
just
kit.
pushing?
I wouldn't. I
Yes, I don't have a defuse kit. I defuse after you. I have
You
time.
did have the defuse kit. I saw it on your head. You have the defuse
Where
kit.
is it?
I saw it. Yeah, on your ass. Shit.
Fine.
Let's move out. Staying here. Spotted the bomb carrier. Has 3 left. That makes 2 left. That makes 1 left. Bomb carrier downrange. Bomb has been planted. Terrorists win. Let's make this right as rain. Decoy. I see the bomb. Bomb has been planted. Terrorists win.
What?
Hold your positions. Move it, son. Hold this position. Two guys left. He's got the bomb. Counter-terrorists win. Hold this position. Cover this area. Let's have at it, mate. Hold your positions. Hold your positions. Hold this position. Now that's a no.
Hold your positions. This area. Hold this position. Let's go. Hold this position. Cover this area. Come on, chop, chop. Hold your positions. One less. They're down to two. One left now. Throwing a grenade. Incendiary.
rushing in? Or are we going sneaky beaky like? Can we give them a spanking?
Connected. Channel switched.
Hello.